Okay, so we will start with the next module, and in the next module we are going to do analysis of LTI models. Okay, and what LTI means is linear time invariant. Okay, all the models that we have basically covered so far, well, not all the models, we have also covered nonlinear models very briefly, but pretty much the last 3 weeks the models that we have been talking about, finite step response models, state space models, in the form that we had written them, come under the LTI models. Okay. Primarily the three things that we are going to talk about is stability, controllability, and observability. Okay. And we are going to talk of all of these in the context of state space models. This is the discrete time state space model. Before we do that, we will do coordinate transformation. We will define a transformation matrix Z, transformation matrix T. The only requirement with respect to T is that the T should be a full rank matrix. Okay. In other words, the vectors that comprise the T matrix should be linearly independent, which also means that T is an invertible matrix. Okay. So, okay, both these conditions together mean that T is a n cross n invertible matrix. What that means is, let us say we are working in an n dimensional space and we have m linearly independent vectors where m is less than n, okay, then the second condition does not work, full rank condition does not work, right. What you need is, you need exactly n number of linearly independent vectors, and when you have n number of linearly independent vectors, they can form the basis set for that Rn space. If they can form the basis set for the Rn space, you can do the transformation to that basis set, okay. And that is exactly what you did in your quiz, and the idea is that you would be able to write a new state, you can define a new state z such that x equal to tz. Okay. How x equal to tz? We have done that in module 1, right, in the first week on linear algebra, right. So, we had talked about doing representing a coordinate transformation as a matrix multiplication, right. So, which this simply means that z we can write this as T inverse x, oh sorry, z equal to Tx. So, we can write x equal to T inverse z, okay. So, when you have x equal to T inverse z, you can substitute that in this state space model. So, you will have T inverse z k plus 1 equal to A T inverse z k plus B U k okay, can have this, and this we can see that this is nothing but a similarity transform. Okay, we talked about similarity transform. There are various properties of similarity transform. One of the main properties is that the eigenvalues of two similar matrices remain the same. So, you would be able to write this as okay. So, now this A bar and this A, these are similar matrices. Okay. That is the property that we had kind of used when we talked about taking an exponent of a matrix. We did a similarity transform where the transformation matrix was nothing but a matrix of eigenvectors, linearly independent eigenvectors. So, that is what we had done in order to do the similarity to do the matrix exponent. Okay, and you will see later where this particular concept becomes very useful.